Welcome everyone to Ancient Mathematics 2. My name is Lady Leonor da Costa, and I am here wearing the funerary headdress of Queen Puabi of in honor of our topic today, Ancient Mathematics. This is class 2. Class 1 will walk you through the numeration systems of Babylonian and Egyptian mathematics. It is a prerequisite for this class, although you probably will be able to follow along even if you didn't quite catch everything in there. So our objective in this class is to try some of those computation methods that I alluded to in the first class. This is the class for people who actually enjoy doing math. I try to keep my classes accessible for people who do not enjoy doing math, but for those who do, this is your class. This one's for you. All right, so let's take a look at Babylonian mathematics, and let's recall that they're using a sexagesimal system, a base 60 system, and their numerals look something like this, where they're using 10 as a sub base, so that after 9 they go to a sideways wedge that marks 10. And so 10s are marked with sideways wedges and 1s with vertical wedges up until you get to 59. And then 60 looks exactly the same as 1 in the earlier periods. Later, they add a placeholder 0, but for a lot of that time, they do not have any kind of 0. And so you just have to infer from the context what number it is, whether it's 1 or 60 or 3600 that they mean. This makes it very difficult to understand which mathematical tablets are doing what. We're going to use modern notation because PowerPoint doesn't do cuneiform. I could not find a font for that. So we're just going to use modern notation, which might be easier for you to work with anyway. And so when we do base 60 notation with our modern numerals, we indicate place values by a comma. We separate them by a comma. So if we see 2 comma 45, that's 2 60s plus 45. What we call the fractions, I guess you could call it sexagesimal. They're sexagesimal fractions, but instead of a decimal point, we now have a sexagesimal point. And that's a semicolon. We're using a semicolon for that. So if we see 3 semicolon 15, that's 3 plus 15 60ths. So that would be 3 1/4 in our notation. Let's give it a try. This one's going to be full of exercises. So try to convert these numbers in sexagesimal to decimal notation. Let's give it a try. And we can talk through it if you want. We're just going to take a minute.
So decimals or fractions? Because 17 is not divided by 6. Can't.
No, but remember, this is 5 60ths and 17, or 5 60s and 17 ones. See, like this?
Oh, it was a comma, not a
semicolon. That was a comma, right. This one's
Never
a fraction, 8, 21, 5.
Yeah, I figured you wouldn't do that to us, but you know.
I'm like I tell my students, I don't assign them homework because I'm a sadistic bee. I mean, I am a sadistic bee, but that's not why.
Can you go back one page for a second?
Sure.
Just to wrap my head around something, that's all.
Absolutely.
Okay. Thank you.
We also have the handouts in the folder if you want to have something next to you to refer to.
Can you post that link again?
Absolutely.
You did it about 3 seconds before I got in.
There it is. There's the link for the handouts. So when we see 5 comma 17, that's a place. That's another decimal place, and then the sexagesimal point is the semicolon. And I gave you easy fractions this time. This time. I wish I had some like Babylonian music to play for you.
I feel like my students. I'm like, teacher, teacher, is this right?
But you can say it. I'm a
It's
teacher.
a great string instrument class earlier.
Oh, yeah. Unfortunately, for some of these ancient cultures, we just have no idea what their music would have sounded like.
Well, that means you can play anything you want. We won't know any better.
Well, yeah, that's why we do ancient cultures, because you can do what you want and just say it's your interpolation.
Just play Istanbul, not Constantinople, and it'll cover everything, right?
I think that's a little further west.
Hmm. I'm thinking about future classes. I know that there's going to be some demand for the abacus class. And I had actually started making slides for that, but then school.
Uh,
I have a geometry class that I've taught before. And then I have, actually have a couple. I have here's looking at Euclid, and I have
oh,
geometry of the Alhambra.
there's a book. Isn't there a book called Here's Looking
I'm
at You?
sure there is. I'm sure I'm not the first person to make that pun. Euclid's probably turning over in his grave right now.
How do you want us to signal that we have
You-
finished our work?
you have
since
all
you
five?
already put the pencils down? Yes. Well, I think I have all five.
Yeah, same.
All right, should we take a look?
I'm done.
You're
Yep.
done? All right, let's do this. Are these the answers you got?
Yeah, I couldn't come up with 1/12 to save my life, but yeah,
Okay.
just having one of those days.
Yeah, I feel that. But did you get all the rest of them?
Yeah.
Okay, anybody else get 100%?
I did if you allow mixed fractions.
Yeah,
Yeah, I got him.
you got them all?
I did too.
Good, well, you should have them all now once you, now that you've
4
seen
or
the
5.
answer. All right, so
I don't have anything.
you don't have anything?
Well, I have arithmetic mistakes from brain fog. But
Gotcha. Okay. Well, but the good thing is this is not for a grade. I know because they're always saying, teacher, does this affect my grade? No, it does
Yeah.
not. It does not. Okay.
Here in my classroom.
Okay. So let's talk a little bit about base 60. I had given you some fractions that reduced, right? 5/60ths is a nice fraction. It reduces down to 1/12. But not every fraction is going to work that way with a base of 60. 60 is a nice base for this because a lot of fractions will reduce. So like, you know, 1/60th of course doesn't reduce, but 2/60ths does, 3/60ths does, 4/60ths does, 5/60ths does, 6/60ths does, 7 doesn't, 8 does, 9 does, 10 does, you know what I'm saying? Like a lot of the numbers between 1 and 60, if you put them in the numerator with a denominator of 60, are going to reduce. So that's one of the advantages of having 60 as a base. However, it has some disadvantages, one of which is that it's really, really large and you can't get away without a sub base. See, 10, you can kind of get away without a sub base if you need to, but 60, you can't read 60 cuneiform wedges. You have to have a sub base. Having a base of 62 when you don't have a placeholder 0 makes it a little easier to infer order of magnitude. So because they didn't have a placeholder 0, right? So if it said that you had 2 wedges goats that you bought from your neighbor, it's probably 2 goats you bought from your neighbor and not like 120 goats, unless you're kind of rich and your neighbor's kind of rich. But it could very well be, you know, 7,200 goats if it's tribute. So, you know, it just depends on the context. You have to infer from the context what the numbers mean. Unfortunately, some of the contexts on the tablets that we see are kind of vague. Like if we can figure out enough to know that it's a table of Pythagorean triples, then we can figure out what order of magnitude it's supposed to be, but a little more difficult when it's like tax records. So. Babylonian mathematics relies pretty heavily on tables. We know this because we found these tables and we've found some of the formulas that they use that relied on these tables. But the disadvantage of tables is that they make arithmetic really kludgy. It takes longer than our arithmetic does today, which is why we use the system we do today instead of sticking with the Babylonian system. If the Babylonian system were superior to ours would never have become widespread. Like, who the heck wants to use an inferior system just because? So that's why their systems and the Egyptian systems have been superseded by our decimal system, because it's actually a faster one. In fact, if you ever look up Margarita Philosophica, there's a woodcut there that shows arithmetic hosting a competition between Pythagoras and Boethius. Don't get me started on all the anachronisms in this woodcut, but anyway, Boethius is using the modern figures, our modern decimal digits and fractions, while Pythagoras is using a counting board, and you can tell who arithmetic favors because you can see the symbols on her dress. So it's because that our algorithms are faster. So be aware that it's going to get kludgy. And for those of you who are like my age or older, I'm 49, you may have grown up using tables of logarithms. Think about how long it took us to do logarithms versus how long it takes our students where they punch it into their calculator and get it. That's kind of the difference I'm thinking of.
I pull that book out once a year so that they know that they don't want to not have their calculator for the next test.
I do too. So also they had this emphasis on practical mathematics rather than theoretical. A lot of the math that we try to like balance practical and theoretical mathematics in our modern courses, but they did not have theoretical mathematics at that time. All math served a purpose, and that purpose was not to, you know, give Theon of Alexandria something to do while he stuck his thumb up his seat. But no, these were actually useful for surveying and things like that. So if they had a fraction like 7/60ths that did not reduce nicely, they would use an approximation for it, and they saw no problem with that, just like my students. They could also take square roots to some degree of accuracy, probably about 4 decimal place accuracy. I'm not going to go into the square root algorithms because most people aren't familiar with the Western square root algorithms. I actually have some more modern square root algorithms in my book. I have a book that my grandpa used to teach himself math. It does have a square root algorithm in it because he grew up in the days before calculators, but yeah, I'm not going to go. It's basically they use the method of false position. They start with an estimate and iterate it until they get the desired approximation. Yes, definitely. Our calculator has a square root key for a reason. So they had a couple different formulas for multiplications. So I'm going to give you a formula, one of their formulas. They had tables of perfect squares. And one of the reasons they had tables of perfect squares is because it made it so that they did not have to have tables for every multiplication there is. Okay. They would just square the numbers. And then they would put it in a formula like this. So if they wanted to multiply two numbers, they would add them together and square them, subtract them and square that, subtract those two and divide by 4. I leave it as an exercise to the reader to prove that that is the same as A times B. So here's an example of that calculation. If they wanted to do 17 times 13, they would do 17 plus 13, which is 30. And then 17 minus 13 is 4. So 30 squared, look it up, minus 4 squared, look it up, do the subtraction, which is actually pretty easy to do in cuneiform. You just take wedges away, or you can use an abacus. And then divide that by 4. We'll talk in a bit about how they did the division. Give it a try. See if you can do 19 times 7.
Can we leave the answer as a fraction?
Yes, you can leave the answer as a fraction, but it should turn out to be a whole number. Since 19 and 7 are natural numbers, the answer should be a natural number as well. Let me know when you have it.
Got it.
Okay. Okay, we got a couple people done. Takes longer, doesn't it, than just multiplying it with our algorithm. It would take even longer if you had to do the perfect squares by hand instead of looking them up on a table.
Well, the first one was 26 squared, right?
Yeah.
I think I screwed it up 3 times in a row
Oh,
because I'm trying not to use the calculator next to me.
gotcha.
So I came up with something with a half. So I think I'm off.
Yeah.
Oh, you know, if I learned to write, it would help.
Yeah, I got it wrong twice from trying to do 19 minus 7 in my head and getting it wrong. But when I did it with the calculator, then I could do it.
19 minus 7 would be where my students screw this up.
Yep.
That's where I screwed it up too. Thank you for telling me. I was sitting there looking for my error.
My students would do a squared plus b squared. They would distribute that exponent, even though I tell them not to do that. I had to resort to when they cancel add-ins with factors. I had to resort to asking them why they hate kittens.
Oh, I show the exact same pictures.
Like I
Helps
have
to
a
be
little
old
poster.
enough. It helps to be old enough that you did math before calculators.
Yes, yes, it does. But every time I have a little poster that has a sad kitten. It says, every time you cancel add-ins, a kitten dies. And
Every
I'll
time
write it
you
on their
miss,
exams. Why do you hate kittens?
every time you take a plus b and write a squared plus b squared,
Yeah.
a small puppy gets kicked.
Yep.
I'll tell you what, guys. I'm not a huge fan of the rays in elementary, but now that I'm starting to see kids who've come up with Common Core,
Mm.
Oh,
that-
please don't
under-
use those foul words.
Common Core is beyond the scope of this class.
That is correct.
All right.
Yeah, the Common Core is evil.
All right. Has everybody got it? We ready to see the solution?
yeah, I'm good.
Here we go. Oh, I guess I didn't put a solution slide. What'd you get? I thought I proofread this morning, but maybe the solution slide disappeared.
38.
133.
133.
Yeah.
Yeah, you should be getting
133.
something bigger than 38.
133.
Oh, I'm
Oh.
sorry. I divided by 4 twice.
Oh,
Whoops.
yeah, only do it once.
Oh.
Okay.
But yeah, I had
Poor kittens.
676 minus 144
Yep.
for the intermediate, and then divide that by 4.
Yep.
That's what and then I divided by again. God.
Yep. All right. So the way they did division, they did not have a long division algorithm like we do. So in order to do division, they multiplied times the reciprocal. So in order to do that, they needed a table of reciprocals. And so that's what these tables of reciprocals they find are for, especially since they were using sexagesimal fractions. So this is not something that like is going to come right to our minds when we think about like, well, what's the reciprocal of something in base 60? That's like brain goes, danger, Will Robinson, danger, danger. But yeah, if they don't have common factors with 60, then they have approximations for their reciprocals. So they didn't, like I said, they didn't care about exact values. They just wanted a number. We're not going to do any division today because I don't have a table of reciprocals for you right now, but let's move on to quadratic equations. So this is a Babylonian quadratic formula. Be aware that they recognized equations that were of the form x squared plus bx equals c. And c had to be a positive number, but b did not. They didn't have the concept of negative numbers, but they did have the concept of subtraction. And so remember that in the past, all problems were word problems. And they would say, the square of something minus this times the unknown. So they could subtract things, they just didn't have negative numbers. All equations of this form where c is positive have 2 real roots. They can't have complex roots. So they're all going to have solutions. They ignored negative roots because they did not have negative numbers. And but the coefficients also did not have to be integers. So that means that they can solve equations with a not equal to 0. But you'll notice that, of course, that coefficient of the x squared term does not appear, because if you allow b and c to be fractions, then you don't need a. But this is their version of the quadratic formula, negative b over 2 plus square root of b over 2 squared plus c. And I leave it as an exercise to the reader to prove that this is equivalent to our quadratic formula.
You said a, they could do it with a equals 0. Did you mean a?
No, with a
equals
not
1?
equal to 1, sorry.
No, okay, all right. That's okay.
I taught math all week, okay.
Welcome to my world.
Yeah, I know.
If you work that backwards, you end up with completing the square, don't you?
Yeah, you do.
All right.
Just as you do with the quadratic formula. So let's try it. Here's a quadratic equation in the form that they would have had it in, x squared minus 3x equals 10. There's your quadratic formula. Give it a try. Solve the quadratic equation the Babylonian way. If you want the full quadratic formula that also produces negative roots, you need medieval India. That's the earliest appearance of a quadratic formula that can find all positive and negative real roots. No complex roots, though. Only reals.
I have an answer. No guarantee it's right.
Plug it back in and make sure it works.
Yeah.
Mine does.
Yeah, well, I hadn't gotten that far yet.
Says the rocket scientist.
I did it both. I did it the old school way of, factoring it just to get the roots.
Yep.
But then I actually just ran it and I went, it's interesting that the positive root is the one that they've done, but not the negative one, because they don't see it as a negative, right? So
nope.
It's kind of cool.
You must have constructed this to give an easy answer.
Yeah, this is actually this exact quadratic I have given to my 4 classes of college algebra kids several times now. So if they can't solve this one, I'm going to hurt them. Not just kidding. I don't hurt children.
I mean, it does make it does make the check back easier.
Yeah, it does. Because I know what the answers are. Oh, goodness.
Well, what's interesting is you have to actually know how to do fractions, which when I ran into problems with kids in 11th grade or whatever it was always, so remember back in grade 3 when we learned about fractions?
Yeah, and of course they didn't learn about fractions in grade 3 because they gave them a calculator. Like, in the future, they're always going to have a calculator. So let's kick them in the kneecaps so they can't do rational expressions.
And I'm going, well, the last time I checked, we still slice a pizza in eighths, but
Of course, then I actually do a pizza project with my trig classes, and I show them this video of this British girl who was saying that she wants her large pizza cut into 8 pieces, not 12, because she can eat 8 pieces, but she doesn't think she could eat 12.
Ouch.
It's the whole pizza.
No.
I may need that video.
Okay.
Okay.
No. Drive the kids crazy and try and challenge them to try and figure out how to cut a pizza into 7 pieces.
All right. You want to see the solution?
It's easier it's harder if you say 7 equal pieces.
This is true.
Okay, yes.
You just said 7 pieces. You didn't say they had to be equal.
Yeah, 7 pieces of any particular size is easy.
Yeah. You can just make 6 parallel cuts.
Mm-hmm.
Of course, I'm the
and
same
then you'll get
person
the
that
wise ass student who cuts it into 6 pieces and said the 7th piece has the size of 0.
Yes.
That probably would have been me.
Yep. All right, so we ready for the solution?
Yes, ma'am.
There you go. So dividing things by 2 is actually not that hard in in ancient or in modern mathematics. We're going to look at in the Egyptian section, we're going to look at doubling and halving. And in fact, if you look at like medieval and Renaissance arithmetic textbooks, you'll see that they have, as part of the arithmetic course, doubling and halving algorithms. And it's exactly because formulas like this were still in use in some places. Get it right?
Yep.
Yes.
All right.
Yeah.
All right, let's move on to Egyptian mathematics. So just as a quick review, their numeration system looks something like this. We are not going to use their numerals, but I want you to understand something about this numeration system, and that is that it makes it really easy to add and subtract. Because all you do is just, if you were going to add, you know, a couple of tens to that, you just bump them lump them in with the other tens, right? And then if you need to carry, you can. If you get 10 of the same symbol, you just cross them out and replace them with one of the bigger symbol. So you can do that. Another thing that's really easy to do in this numeration system is to multiply things by 10. All you do is just replace all the coils of rope with lily pads, all the hobbles with coils of rope, and all the ones with hobbles. So not too bad, right? Easy enough. So that's how you do addition and subtraction. Give it a try. See if you can do 54 plus 78 in their notation. And this is a little easier to do in their notation than it would be to do in Babylonian notation, just because it's base 10 like ours. So we're on more familiar cognitive territory. See if you can do that, 54 plus 78. I deliberately chose a problem with easier symbols to write, so you don't have to sit there drawing lily pads all day. Or fingers, or guys with their hands in the air.
And if I remember from the last class, you said order doesn't matter.
Correct, because this is not a positional system. So if you wanted to do 54, you could do 5 hobbles and 4 ones, or you could do 4 ones and 5 hobbles, or you could mix them up a little. You could do it how you want. But it just makes it easier if you're collecting all of the same symbol in one spot. And for those who've used a counting board, this is going to be very similar to how you use a counting board. The Egyptians had abacuses too. When you have an abacus, you only have to write down numerals. You don't have to do computations with numerals like we do. Did you get it?
Done. We'll see if it's right.
Okay.
5 characters, right?
Well, did you get 5 characters?
I did.
I did.
I got 6.
I got 6. So someone is wrong.
That would be me, I'm certain. Oh, it should be 6, because you know, if I write them all down, it would help.
Oh yeah, if you write them all down, sure.
Yeah.
All right. So you see how that goes? It's not that hard, right? You have to carry. You can borrow too to do subtraction in the same way, just kind of like if you changed a $10 bill for 10 ones. So to do their multiplication, this is a really cool algorithm, and this is a great one for if you're, because I'm teaching an adult class in ethnomathematics for my district. And one of the things we're trying to do is bring other mathematical lenses into the classroom. And so one of the more accessible ones is Egyptian multiplication. And this one may make sense to students whose brains don't work in the conventional way with the numerals we have. But in order to do the multiplication algorithm, you have to be able to double and to multiply by 10. And so these are actually pretty easy to do. It's easy to double numbers in our notation if you do it right to left. And you also still can do it going left to right. It's just a little bit different because you might have to change a digit here and there. But the basic idea when you're doubling, if you're in Egyptian notation, you're just going to write twice as many symbols. And if you get more than 9 of any symbol, you just exchange them. You carry, basically. To double in our decimal notation, you double a digit and then you double the next one. And if the next one is more than 5, you're going to add 1 to the, or 5 or more, you're going to add 1 to the one you just did. So it's also real easy to multiply by 10. In our notation, we just put a 0 on the end. So they can, with using this technique, they can ditch the multiplication tables that that the Babylonians had. So it makes them faster with their multiplications. So let me show you how this works. We're going to do 82 times 17. 82 is the bigger number, so we're going to double 82. So we're going to start with 82 times 1, and then we're going to double it. We're going to double 1, that gives us 2. We're going to double 82. 8 times 2 is 16. 2 times 2 is 4. So we're just going to double each of those. Okay, and then we're going to double again. So the next row will be 4 and what?
$328.
328, good. And then the next one?
Would give you 656.
8 and 656. And then the next one?
1312.
16 and 1312. Okay, now if we were to go one more step, that would be 32, but 32 is bigger than 17. 17 is our other multiplicand, right? Our smaller multiplicand. So, so we're not going to go past 16 because we don't need to. Now, for fans of binary, you're going to recognize what I do next. Okay, I'm going to mark the numbers. I'm going to put a little star, check mark, or whatever, some kind of mark by the numbers that add up to in this column here, the 1, 2, 4, 8, 16 column that add up to 17. I'm basically finding 17 in binary. And then you can either cross out the ones you're not using, or you can use a 4th column and copy over only the ones you're using. And then you just add them up, and that gives you your product. Pretty cool, huh? It's an interesting way to introduce younger students to the concepts of binary as well.
How long did you say you were exposed to this thing?
So try it. Multiply 23 by 11. Remember, you can double and you can multiply by 10.
Do we need to go? I should be able to figure this out. Do we need to go to just use 2 numbers on the left, or could we use a combination of numbers?
You can use any combination. As long as that combination adds up to 11.
I'm pretty sure Charlie had the same all right. Third state.
It's just the one that I did in the example happened to use 2 of the 5. But it's possible to use all of them, or even just one of them.
Or 3 of them even.
or 3 of them, or 2 of them. You'll see how easy doubling is. It's pretty straightforward and easy in any kind of decimal notation. Well, I guess it's easy in other notations too, but where decimal notation is our familiar ground, it's easy for us.
Yeah, I can see how that works.
Yeah, it's pretty cool, huh? Did you get the answer?
I did, but I don't want to
You don't want to give it away for those
give it
still
away
looking,
until
huh?
you do
Likewise.
for the teacher.
Okay.
230 plus 23.
Yeah.
We ready for solutions?
Yes.
All right. Solution number 1. If you do it the binary way with just doubling, you're going to add the 1 and 2 and 8 lines and get 253. If you want to be clever and multiply by 10, you can do it in 2. You get the same answer though. Oh shoot, I forgot to change that one column. Okay, yeah, it's I'll change it.
Just go
for
back
you.
to column 3.
Yeah, I go back, refer back to column 3. All right.
Dale, you're out of teaching.
Okay. Sorry, I was proofreading this morning and I had the caffeine hadn't fully kicked in yet. So so now let's talk about Egyptian fractions, because this was actually the world standard fraction system. Fibonacci wrote on this system, because even as late as Fibonacci, they were still using the Egyptian system. The decimal fractions took over not terribly long after that, though. So because they were just a better system. But Egyptian fractions are also known as unit fractions, so that they're fractions with a numerator of 1. The Egyptians also used 2/3. They had a special symbol for that. To make the notation for a fraction, they would take the number that was the denominator and put a little kind of an open almond shape, almost like an eye shape, but without an eyeball. Over it. So, but when we write Egyptian fractions, we tend to write them with a bar over them. And that doesn't mean like when we say 0.3 bar, we mean 0.3333333333333. But this means 1/2 instead. If we just take a 2 and put a bar over it, that means it's 1/2. It's a unit fraction notation. They're very kludgy. They're table based. So you have to have tables in order to do Egyptian fractions. There is a theorem modernly proved that you can express all fractions as a finite Egyptian fraction expansion. However, they did not necessarily know that back then, except by practical experience. Well, of course, all fractions are a decimal or fraction expansion, because if they didn't get it exactly, they'd get it approximately, and they didn't see the difference. So, but it is possible to express all fractions as a finite terminating expansion of Egyptian fractions. So let me give you an example of what that would look like. So 3/4 is 1/2 plus 1/4. Kind of like that. So see if you can find an expansion for 7/8 and an expansion for 5/6. I've given you some easy ones because I'm not giving you a table.
Those are pretty cool.
Yeah, you got it?
Yeah.
Okay.
It's like the opposite of what my students would try to do.
Yeah. Well, because they're not ancient Egyptians.
Well, because they're also, well, we got the answer. Why would we need to add things?
Yeah.
So
And then, of course, if you had a fraction and you wanted to divide it by a number, you could do the fraction division. So, for example, if you took 3/4 and you wanted to divide it by 7, you'd do a half divided by 7 plus a fourth divided by 7. So then you'd have 1/14 and 1 plus 1/28.
now that's a cool expansion of this. I like
It
that.
is. And we're not going to have time to do like every single operation that each of the
Oh yeah,
cultures
because
did.
we're pretty close.
Yeah, we're close to
right
time.
now,
This
so.
is the last.
You don't happen to have, are you using, I don't want to take up everybody's time
Hmm?
if they're done working.
Is everybody done working?
Yes,
Yep.
Ready for the answer?
Yep.
There it is. Did you get it right?
Yep.
Yep.
yeah.
Okay.
They wouldn't do it with subtraction.
They would. Well, the
One
Egyptian
minus an
fraction
eighth.
system is just pluses. Everything is expressed as a sum of Egyptian fractions.
Okay.
But they wouldn't say 5/6. They'd say 5 divided by 6 is 1/2 plus 1/3.
When would subtraction have come in?
You could subtract 2 divisions. So you could do 7 divided by 8 minus 5 divided by 6. And then you can subtract those component fractions. So you could do the 1/2 minus the 1/2 and they cancel each other out. But then you'd have to figure out how to do 1/4 plus 1/8 minus a third. And that you'd have to look up.
So subtraction was something that they did in fact already use.
Yeah.
I just didn't know if it came in about the same time as addition. So
They can do full arithmetic with subtraction. They had to look up fractions on tables to do it. Questions?
this is super cool. Thank you. Thank you for
Oh.
coming all the way from Colorado to do this for us.
All the way from to my dining room. Huh?
It's a cool, it's a cool set of stuff, right?
Yep.
So, thanks.
And it's not horrible. You just have to remember that you can do it.
Yeah, it's just
You
different.
have the time. Yeah.
And for those of us who know the ways of the real numbers, it's a little easier to understand than for people who do not. Like, for example, we know about the associative law and the commutative law and the distributive law and all of those. But, back then they didn't have those formulated as laws, and we didn't, like, our students kind of don't understand them fully either, not as fully as we do. So, yeah, it can get a little difficult to get students to understand them, but it's fun for the adults.
Could you go back to the last slide, please?
Absolutely.
I'm trying to see how you do the lower one without converting them to sixths. And that's not 1 over a denominator.
The first step I took was I went, all right, if I can make a half, then I'll deal with what's left over. And so I split it into 3/6 and looked what was left over, and it helped.
Yeah.
Yes, but you have to turn it into 3/6, which is not 1 over a denominator.
They would have this on the fraction table.
Ah, okay.
I made
That's
you
why I was
guys do it by
curious, because
hand.
you
with
said they did
units.
everything with 1 over a number. I
Right.
didn't see how you could do that with 1 over a number without converting into something like 3/6 and 2/6.
So the context in which a lot of these problems come up on the papyri is inheritance problems. So like one person is supposed to get you know, a 17th of the inheritance, and another one is supposed to get a 1/6 of the inheritance. And then they also have like a son who has to get twice as much as the daughter. And, you know, I mean, it's problems like that. So that's the context in which you see these on the papyri.
Okay.
Please make sure, if you have not at the beginning of the class, to put your SCA name in the chat so that I can take roll and get you credit. Thank you very much, everybody. I appreciate you coming out to do nerd stuff with me.
Thank you.
Oh, this is super cool. Thank you so much.
Thank you.
Yes, thank you.
You